Load distribution engineering marvel. When a 6,000-ton freight train thunders over railway tracks, the forces involved will crush most surfaces, but ballast stones perform an engineering miracle. The weight of these massive locomotives and their cargo creates pressures that would devastate concrete, asphalt, or virtually any other surface material. A single freight car loaded with iron ore can weigh 125 tons, and modern freight trains routinely pull 100 or more of these cars. The total weight pressing down on the rails reaches levels that would cause immediate structural failure in most construction materials. Yet ballast stones handle these enormous loads day after day, year after year, without catastrophic failure. The load distribution mechanism works through a principle called stress diffusion, where concentrated wheel loads spread outward through the stone matrix. Engineers use mathematical models to calculate how forces propagate through granular materials like ballast. The stress diffusion follows predictable patterns based on soil mechanics principles developed over decades of research. When a train wheel applies force to a rail, that force transfers to the rail to the sleeper below. The sleeper then applies that concentrated force to a relatively small area of ballast stones directly beneath it. These stones immediately begin distributing the load to neighboring stones through their contact points. Each railway sleeper concentrates the weight of an entire train car into a relatively small contact area, creating pressures that would exceed the bearing capacity of most soils. A typical concrete sleeper measures approximately 2.5 meters long and 0.3 meters wide, creating a contact area of roughly 0.75 square meters with the ballast below. When a 125-ton freight car passes overhead, this sleeper must transfer that entire weight through its small contact area. The resulting pressure can reach 15 to 20 tons per square meter directly beneath the sleeper. Natural soil can typically support only 2 to 5 tons per square meter before failing, making direct placement of sleepers on soil impossible for heavy railway operations. The ballast layer acts like a sophisticated load spreading system, taking point loads of up to 25 tons per square meter and distributing them across much larger areas. The load spreading occurs through the natural mechanics of granular materials under compression. As pressure applies to the top layer of stones, these stones compress slightly and transfer forces to stones below and around them. Each successive layer of stone spreads the load over a wider area. By the time forces reach the bottom of the ballast layer, they have spread across areas many times larger than the original contact area. This spreading effect reduces pressure on the underlying soil to levels it can safely support. The depth of the ballast layer, typically range from 25 to 30 centimeters, is calculated based on soil-bearing capacity and expected train loads using complex geotechnical formulas. Engineers use the Boussinesq equation and other stress distribution formulas to determine optimal ballast depth for specific conditions. Soil-bearing capacity testing involves taking core samples and conducting laboratory tests to measure how much pressure the soil can withstand. Train load calculations consider not just static weight, but also dynamic forces from acceleration, braking, and track irregularities. The formulas account for safety factors that ensure the ballast system can handle loads significantly higher than normal operating conditions. Advanced finite element analysis shows how load distribution efficiency depends on stone size gradation, with specific ratios of large to small stones optimizing the spreading effect. Computer modeling divides the ballast layer into thousands of small elements and calculates stress distribution to each element. These models reveal that uniform stone sizes create less effective load distribution than carefully graded mixtures. Large stones provide structural framework and resist major loads, while smaller stones fill gaps and improve contact between larger particles. The optimal gradation typically includes 60% large stones, 35% medium stones, and 5% small stones. This distribution maximizes load spreading while maintaining adequate drainage properties. The void spaces between stones rather than being. Wasted space actually contribute to load distribution by allowing stones to slightly rearrange under pressure. When trains apply loads, the ballast stones compress slightly and rearrange to better distribute forces. This rearrangement allows the stone matrix to adapt to changing load patterns and maintain optimal contact between particles. The void spaces also provide room for this movement without creating permanent deformation. Laboratory testing shows that ballast with proper void ratios can handle 30% higher loads than densely packed ballast with minimal void space. Dynamic loading from moving trains creates additional challenges as the ballast must distribute not just static weight but also impact forces. Moving trains generate impact forces when wheels encounter rail joints, switches, or track irregularities. These impact forces can exceed static loads by factors of 2 or 3. High-speed trains create additional dynamic effects from wheel-rail interaction at elevated speeds. The ballast system must absorb and distribute these dynamic forces without allowing permanent track displacement. Impact forces occur when train wheels encounter discontinuities in the track structure. Rail joints create vertical impacts as wheels transition from one rail section to another. Switch points generate both vertical and lateral impact forces as wheels change direction. Track irregularities from settlement or wear create additional impact loading. These impacts can generate force spikes reaching 40 to 50 tons per square meter instantaneously. The ballast system must distribute these extreme loads quickly enough to prevent damage to underlying structures. The stone matrix accomplishes this through rapid force transmission between interlocked particles. Without proper load distribution, the subgrade soil beneath ballast would fail, leading to track settlement, alignment problems, and potential derailment. Soil failure typically occurs through bearing capacity exceedance or excessive settlement. Bearing capacity failure happens when applied loads exceed the soil's ability to resist shear forces. This type of failure can occur suddenly and create dangerous track conditions. Excessive settlement develops gradually as soil compresses under repeated loading. Settlement creates track geometry problems that require expensive maintenance and can limit train speeds. This load distribution system represents one of the most effective and economical foundation technologies ever developed for heavy infrastructure. The ballast system handles loads comparable to those supported by concrete foundations at a fraction of the cost. Unlike concrete foundations, ballast systems can be easily modified, repaired, or relocated as operational requirements change. The